Hi everyone. In this video, you are going to learn about switch logic. Switch logic and gate logic, these are the two different logic functions which are used to generate or create different types of CMOS logic circuitry. Switch logic already you might have seen in the form of pass transistor logic. So pass transistor logic we have seen, and another gate is transmission gate. So these two gates are commonly known as switch logic. Switch logic is nothing but just used to uh, create different types of logic functions like AND gate, OR gate, NAND gate, NOR gate using the pass transistor logic or transmission gate logic. So these two comes under switch logic. Now, pass transistor logic. What do you mean by pass transistor logic? One transistor is there. This transistor is having a control input here. This transistor is having a control input at this gate terminal, and here is the source terminal and this is the drain terminal. Whatever the input we are giving at this source terminal, that will be coming out onto this drain terminal when the control input is at logic high, if it is an NMOS transistor. Okay, if it is an NMOS transistor, the control input, if it is 1, then input will be transferred to the output. If control input is equal to 0, then there is no output because it acts as a open circuit or high impedance circuit. Okay, so this is what the pass transistor logic. You will see, of course, diagrammatically. And another one is transmission gate. A transmission gate is nothing but we have a drawback with respect to the pass transistor logic that can be avoided using this transmission gate. Okay, I will explain individually when we go into these topics. Coming to this pass transistor logic, first one, pass transistor logic is having a series of pass transistors. What I explained, pass transistor is nothing but a single transistor is there with a control input, and input will be transferred to the output when control input says at logic 1. Now we are taking a similar set of pass transistor logic where 4 different transistors we have considered in the first case. All these 4 different transistors are applied with the control inputs A, B, C, D. Now here is the input we have given and this is the output. Now output V out is equal to V in when all the control inputs A, B, C, D is equal to 1. A dot B dot C dot is equal to 1. That means A into B into C into D is equal to 1. That means if any one control input becomes 0, then the output is 0. Okay. In the similar way, just the same is extended with an inverter. Like say up to here we are getting, when all these A, B, C, D equal to 1, we are getting V input here, and this will be complemented after passing through this inverter V in bar, and again when E, F, G, H control inputs is equal to 1, this again V in bar will reach here and again coming as V in. So V output is equal to V in. V output is equal to V in when all these control inputs are set to be at logic high. At logic high. And V out is equal to, simply we can say, high impedance or open circuit. Then when if any one of these control inputs is equal to 0. This is what the pass transistor logic. Okay, simply one control input is there, input and output. Output is equal to input when control input is equal to high. Output is equal to nothing, 0, then when control input is 0. Okay. Now there is a drawback with this pass transistor logic. What is that drawback? See here, the properties of pass transistor and transmission gate. That means why we are going from pass transistor to the transmission gate. Here it is clearly explained. Suppose if you are taking an NMOS transistor, observe clearly, this is NMOS transistor. This NMOS transistor is having input on the left hand side and this is the output. And we are giving the control input X. Here X is taken as the control input. X is equal to plus 5 volts. That means NMOS transistor is said to be in on state. NMOS transistor is said to be in on state. Now take a logic from 0 to 5 volts at the input. Take this logic level from 0 to 5 volts at the input. As this transistor is in on state, the same will be at the output. Ideally, we are expecting that there will be a change of 0 to 5 volts in the output. But the transistor, when NMOS transistor is said to be operated in on state, it is having a drop across this, which is nothing but threshold voltage Vt. Vt is the threshold voltage, that is the drop across this transistor, because on transistor is replaced by a resistor. That resistor is simply having a voltage drop across it. So after reduction of this voltage drop, the remaining voltage will be going to the output. So that's why there is no change in the logic 0 level, because when transistor is in off state, output is equal to 0. When transistor is in on state, then output is reduced by an amount of Vt, threshold voltage of the pass transistor, VTP, for the NMOS transistor. Hope you understand. Threshold voltage of the pass transistor for NMOS transistor, there is a reduction of this amount. Initially we have to get 5 volts, but now it is reduced to 4 volts. So the logic level will be 0 to 4 volts. That Vt is equal to 1 volt. Okay, this is the problem with respect to the pass transistor in the NMOS logic from 0 to 5 volts. And see here, N switch degraded logic 1. Degraded logic 1, that means we are not getting 100% logic 1. Logic 1 is degraded by an amount of threshold voltage, so that's why degraded logic 1 we are getting in the case of NMOS transistors. Now apply the same case with respect to the PMOS transistor. So PMOS transistor is having 0 as the control input to make the transistor on, because it is a PMOS transistor having the bubble. So that's why X bar we are giving, X bar, that is equal to 0 volts, logic 0, nothing but 0 volts. That makes the transistor in on state. Now PMOS transistor is having negative threshold voltage. PMOS transistor is having negative threshold voltage. That means when input is equal to 0, here also we have considered 0 to 5 volts at the input. When input is equal to 0, 0 minus of minus Vt, so 0 plus Vt, that is the output. So even when input is equal to 0, there is an output of plus 1 volt, plus 1 volt. That 1 volt refers to threshold voltage of the pass transistor. Threshold voltage of the pass transistor for PMOS transistor. In brackets P is there, that is nothing but PMOS transistor. Okay, so this refers to there is a degradation in the logic 0. There is a degradation in the logic 0 for the PMOS transistor. Okay, but we have, when we see the logic high level is having the same level plus 5 volts, but degraded logic 0, we are not getting 100% logic 0, we are getting some 1 volt is the minimum value. But in the case of NMOS transistor, we are getting 100% 0 voltage, but we are not getting 100% logic 1 level. So if you see properly these two, logic NMOS transistor is degraded in logic 1 and PMOS transistor is degraded in logic 0. So if you combine these two, we may have a logic function 0 to 5 volts completely. Okay, that is the reason why we are going to the transmission gates. Okay, transmission gate is having the main purpose of moving to the transmission gate is for getting good logic levels. For getting good logic levels. So good logic levels means logic 0 must be 0 volts and logic 1 must be plus 5 volts without any degradation. This can be possible in the case of transmission gate. So if you see the transmission gate, it is a combination of NMOS and PMOS transistors. See this, in the bottom side if you see, this resembles the PMOS transistor. In the upper part if you see, it will be nothing but an NMOS transistor. Okay, so if we are just combining what we have combined, source and source terminals of the NMOS and PMOS transistors and drain terminals of this NMOS and PMOS transistors. So these two are combined together. Okay, that means whatever the input we are giving 0 to 5 volts, that will be applied commonly to both the source of this NMOS transistor and source of this PMOS transistor. Okay, so that's why the input is after passing through this transmission gate. See the control inputs we are giving. NMOS transistor is set to be on when we are giving plus 5 volts and PMOS transistor is set to be on when we are giving 0 volts. So it is fixed because we are making the transistor transmission gate to on. Now what about the output? See here, if you see the NMOS transistor is suffering from degraded logic 1 and PMOS transistor is suffering from degraded logic 0. So 0 to 5 volts when it is applied to NMOS transistor, we may have plus Vt over there. For NMOS, we are having plus Vt threshold voltage, and for PMOS we are having minus Vt as the threshold voltage. But when you combine these two, at the output you are having addition of these two. At the output you are having addition of these two. That means if you say logic 5 volts, that makes the 5 minus threshold voltage of the NMOS transistor plus this plus means minus of we can say, we can write like this. See here, NMOS transistor is having plus Vt as the threshold voltage, and PMOS transistor is having minus Vt as the threshold voltage. So when you are giving plus 5 volts here, that plus 5 volts after passing through this NMOS transistor, that will be 5 minus of Vt minus this Vt will come. Vt for the PMOS transistor and this Vt for the NMOS transistor. So this one will be cancelled and it will be having only 5 volts. This is the reason why we have combined the transmission gate PMOS and as well as NMOS as a transmission gate. Okay, so plus 5 volts from the NMOS transistor and minus 5 volts, plus Vt from the NMOS transistor and minus Vt from the PMOS transistor. These two are cancelled and giving a good logic function 0 to 5 volts in the output. And if you see the symbolic representation of the transmission gate, this is the symbol. It will be like this. This is the control input for the NMOS transistor. This is the control input for the PMOS transistor, and it is input and output. Okay. Suppose if you more elaborate the pass transistor logic, if you are giving logic 1 here, which is nothing but VDD, that VDD when this transistor is said to be non-state, VDD minus VT, pass transistor logic threshold voltage, so VTP. And again when you are giving the same logic function, it again degraded by amount of VDD minus 2VP, as it is passing through the two different transistors. Okay, so that is the reason why we are not using pass transistors and why we have moved to the transmission gate for getting good logic levels. Next, if you see the logic realizations with respect to the transmission gates, simple realization, it is the transmission gate 1. This transmission gate is having input A from this NMOS transistor and A bar from this PMOS, and it is V1. So what is the output at this particular point? We can say it is A into V1. A into V1. That means if A is equal to 1, output is equal to V1. If A is equal to 0, output equal to 0. And similarly here it is B into V2. Similarly here C V3, and here D V4, and here E V5. So when you combine all these at this particular point, it simply appears like V1A plus V2B plus V3C plus V4D plus V5E. Okay. That means by assuming all A, B, C, D, E are mutually exclusive. Okay. So V out logic levels will not be degraded by any threshold voltage effects because of the transmission gates. This is what the advantage of transmission gate over pass transistor logic. Okay. Thank you.